Hey, good evening. Sorry, just had a school curriculum meeting and then ran a little bit late. All right, so we're gonna finish this multivariable function part with the last topic called total differential. Then we'll start a new topic called grading vector. All right, so this part, total differential, okay, has a lot to do with the concept of a linearization. So let's look at the linearization first, and then I'll lead into the concept of a total differential. Okay, so if you recall, let's start from the simple one here. Start from function single variable. Okay, so let's say if somebody says, okay, can you approximate this function at x equal to 2? Okay, that's a simple question. And we learned in first year, okay, to approximate this function at x equal to 2, we can approximate that using a straight line, right? So we create a tangent line at that location, and anywhere around x equal to 2, using a line, we'll be able to approximate this y equal to f of x. And this line, okay, is y equal to f of a and plus f prime of a x minus a. So this is basically the line equation there. Then, I mean, alternatively, you can see the y here. Right, this y around the actual y, right? This y is referred to the straight line here. So the actual y is approximately this f of a plus f prime of a and x minus a. So you can use the value from the straight line to approximate this curve y equal to f of x. So now let's go to our function of two variables. So let's say you have function two variable. We all know that this will give us a surface. So if I ask the same question, how can we approximate this function at x naught, y naught? So can we find a similar approach to approximate this function at this point? So where is this point? Let's see, this point, this is x naught, y naught. Okay, and that's the corresponding value on the surface, right? So this is your z naught example. Okay. So for the point over here, right? So this point here, let's see, this point here is coordinates x naught, y naught, and then f of x naught, y naught. That's the coordinates for these points on the surface. So if I take a guess, I mean, for a single curve, I could use a straight line or tangent line, right, at that location to approximate this curve. Then if I have a surface, curved surface, and I need to find something to approximate the surface at this location. So instead of a line, what do you think would be a suitable geometry to approximate this surface? Not a line anymore, right? It should be a plane, exactly, right? So you can think about, how about create a tangent plane to the surface at that point? Then I can use this tangent plane, right? You don't use the plane everywhere. You just choose the point close to this x naught, y naught, f of x naught, right? As approximation to the surface. So basically, you can see I could use a tangent plane at x naught, y naught, and then f of x naught, y naught at this location as an approximation. Okay. So now the question is, what would be the plane, right? What does the plane look like? Okay. So we have actually different ways to do that, but today we will use a slightly, in the future, we'll use a slightly different one to find a tangent plane to a surface at a certain point. Okay. But today we use a slightly different approach. So today we can use Taylor series expansion. I'm not getting into too much details here. Taylor series expansion for z equal to f of x, y. And you have learned Taylor series expansion for function single variables. Okay. As a matter of fact, if you look at this left side, the right side of this approximation of the line equation, right? And that's actually Taylor series expansion of a function f of x at x equal to a by taking only the first two terms, by neglecting the higher order terms of Taylor series expansion, then you're going to left with just this straight line equation, right? So similarly, given a function of two variables, you can also expand it using Taylor series expansion approach. So this z, okay, so z, it will be approximately equal to, okay, f x naught, y naught, okay. So now we're talking about at x naught, y naught location, right? And then plus fx, x naught, y naught. So that's first order derivative term, x minus x naught. Right? This is partial f, partial x, and then fy, x naught, y naught, y minus y naught. Right? This is essentially like these two terms here, like the first order term of the Taylor series expansion for function single variables, right? And then this is a constant term, right? So this is the first order term. The reason you have two terms because it's a multivariable function. If it's a single variable, then you only have one single term here, right? Yeah. As you see here, this is your first order term from Taylor series expansion. Okay. So technically, you should add up some of the all higher order terms for Taylor series expansion, but we are getting rid of them. Okay, so that's why you got an approximation equal sign at here. So if you expand the first, the surface z equal to f of x, y using Taylor series expansion by keeping only up to the first order term, then this is what you get. Okay, so what's z, right? I mean, z, so maybe just z equal to f of x, y. That's your original function. Okay, so now, if you look at this one here, if I focus on the right side of this expression, okay, just focus on the right side expression, I'm gonna let's call the whole thing on the right side, use a new symbol. Let's call it function L. So L of x, y. So basically we define ourselves a new function. So instead of calling Z, we call it L just to differentiate. So L x y equal to this. Let's just write it over here. Okay. So your original function f is approximately equal to this L. And L is defined by this whole long expression. So I want you to take a close look at this L here. Okay, so this guy here. What is it? It's a plane, right? It's actually a plane. So remember plane equation, a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. Okay, that's a plane equation. Of course, the z here, we use a z, but now in this case here, we have an L at it here, right? So if I move everything for this expression to the same side, so you look at this. This is basically your A. And this is basically your B. What's the C value here? No? What's the C value? -1. Right? So this one, L here, is basically my Z. And this F here, this is a constant. That's your Z naught, or maybe we should call it L naught, right? In this case. Okay. So my point is, this L expression is basically a plane equation. It has a plane equation. It has a normal vector, which is A, B, and then -1. And it passed through which point? It passed through x naught, y naught, and this z naught, which is the f of x naught here, right? So maybe I should just write here. Normal vector is fx, x naught, y naught, fy, x naught, y naught, and then -1. A point on the plane is x naught, y naught, f of x naught, y naught. Right? And that's what we want. We want the plane to pass through this point and tangent to the surface. Okay, as actually later we're going to learn, well, you'll see this vector here. This is a vector normal to the original surface. Okay, so if this vector normal to the original surface and also normal to the current plane, right? So that plane is tangent to the original surface. Okay, so basically the Taylor's expansion results, okay, if you only keep the first order term, you end up with the plane, which can be used to approximate the original surface function f of xy. So that's the point here. Okay. So this L here, right? This L here, so the L f x y here, sometimes it's called a linearization of z equal to f of xy. So that's why Taylor series expansion, you see it's widely used in linearization. You linearize some nonlinear function into a linear function. Right? You linearize a curve into a straight line. You linearize a surface into a plane. Right? So this is the basic concept of linearization. Okay? So you're changing it to a linear system. Like, okay, so that covers the linearization concept. Okay, but this doesn't cover our total differential concept yet. Okay, so our big title here is total differential. So let's look at what give us the total differential concept. Okay, so let's go back to this equation. Okay, so go back to this equation here, the results of this Taylor series expansion. Okay, then I'm going to move this f of x naught y naught to the right side, to the left side. Okay. So then I will get f of x y. So maybe I should put on a title first. Total differential. Okay. So fxy minus f of x naught y naught is approximately fx x naught y naught x minus x naught plus fy x naught y naught y minus y naught. All right, so I didn't do anything. I just moved one term to the left side. Okay. All right, so what do we end up with here, right? So what you end up here is, you see, you start at the point x naught, y naught, and then you move away to somewhere else to xy location. Then you find the difference between the value of the function f, the new location, and minus the value of the function f at the original or starting location. So this part here, we can call it delta f, right? So the difference. So you move from this location to the next location, there's a difference, right, in the function value, okay, delta f. So delta f is approximately equal to, let's rewrite the left side here, okay, yeah. And then x minus x naught, right? If I call this as delta f, then x minus x naught is like your initial x naught location, you're now at the x location. So I have a delta x change, right? And then the next one, fy x naught y naught, you initial at a y naught location or value, and then you end up with a new y value, so you have a delta y. So that give you a new expression. To appreciate this expression, basically what it tells me is if you start at x naught y naught location, okay, so it's like this. So if you have it started here, okay, then you are initially at this location on the surface, and now you move away from this location to a new location xy. So for the new location, there's a new value on the function on the surface f of x, y, okay, vertically, right? So what is the vertical difference between these two? It's given by the delta f. So now your interpretation of this expression is the change. So basically, this is the change in function f. Right, this is the change in function f is determined by these two terms over here. Right, so approximately, huh? Yeah, this approximately can be calculated using these two expressions. Okay, so Then what happens if x is infinitely close to x naught and y is infinitely close to y naught? So you let x naught, y naught approach to the original x naught, y naught, right? You let x approach this, right? So basically the point is almost right, infinitely close to this original point. Then this is a limit concept, right? This is a limit concept. Whenever you let this close enough, the delta become a straight D, differential. It become differential quantity. Then this expression at here became df equal to fx x naught y naught times dx fy x naught y naught and dy. Right. So this is the result of the so-called total differential. This expression here, as x approaches x and y, not only delta becomes straight D, the approximation sign will become a straight equal sign. Right? That's a limit concept. So this expression is the so-called total differential. Okay. So total differential of a function f of xy, right, at x naught, y naught location. Okay. And I want to relate to a simple case. A similar case is function of single variable. And you take derivative of the function, right? You get df over, let's say, for example, this is x squared. Then you got df over dx equal to x, 2x, right? Okay, yeah. So over here, you can write it as a df equal to 2x dx. And that's function, this is differential. That's function single variable. That differential equal to 2x dx. See the similarity, right? Between this multivariable function here. You just had one more term here. Okay. And of course, we require to take a partial derivative now instead of just a derivative. Okay. And we don't call this total differential. We just call this as a differential. So now you can appreciate where the total comes from, because the df depends on dx and dy. Or in other words, it depends on change in the x, the change in the y. Okay. That's how the differential concept is derived. Okay. So let me write it to df is related to dx to the changes dx and dy. Okay, yeah. So there are a few applications. Okay, mostly actually applications. One a lot of time we use this one as application. Okay, because differential is a very precise concept. Okay, but delta f is approximation concept. Right, so we use this one here a lot of the time to approximate the change of the function when there's a change in the x and y value. So I'll give you an example right away here. Okay, so let's take a look at example of the application of this approximated change. Okay, give ourselves a cone here. The bottom of the cone has a radius r, and it has a height of h. We all know that the volume of the cone is defined by 1/3 of the base area then multiply by the height. So that gives us a volume. So the V basically is a function of R and H. So that's an example of a function two variables. Okay. A very common question like this is, number one, find the total differential dV. And then number two, okay, suppose R goes from 10 centimeter to 10.1 centimeter. H goes from 1 meter to 0.99 meter. And then ask you to, can you find the approximately the change in the volume, delta V? So this is the very typical question for this part of the material. Okay, so let's take a look at together how do we approach this. Okay. So let's first find the total differential. So you go back to your total differential formula. Okay, so this is a total differential formula here, right? Now this total differential formula is a little bit specific. It says the total differential at x naught, y naught. I mean, you could just make it more general. Basically, instead of one specific point, x naught, y naught, it can be replaced, right? So this one can be replaced with just simply df equal to fx dx plus fy dy. Okay, we don't involve any specific location. So that's the question. So let's look at this one here. So what's dv? Now, obviously, you need to calculate two first order partial derivative in order to get this total differential, right? So let me just, let's say number one, dv equal to partial v over partial r dr partial v over partial h dh. So that's your total differential formula. So I need to calculate the two first order partial derivative. Here's your v function. That should be pretty straightforward. You take partial derivative back to r, you take h as a constant, so that's 2 over 3 pi r h. And then partial v partial h, 1/3 pi r square. Okay, so altogether, you put them together, then you get your dv equal to 2/3 pi r h dr plus 1/3 pi r square dh. A very common mistake I see at this part of here is oftentimes students do not write dr dh at here. And that's a mistake. So you got to have a dr dh because it's part of the total differential formula, right? It's a small change. It's a differential change dr, differential change dh. Second part of the question, you are going to calculate the delta V change. So delta V change means you calculate partial V over partial R, but now you need to calculate its value at the initial points, R naught, Y naught, or H naught. And then multiply by delta R, partial V, partial H at the initial location, delta H. So that's approximately change formula. Okay. So you already calculated the two partial derivatives. Okay. So we just have to find what is the initial location R naught, Y H naught. So this is your initial location. So go back to the question here. So R changed from 10 to 10.1. H changed from 1 to 0.99. So your R naught, H naught is 10 and 1. but this is centimeter, this is meter. So I think I need to convert maybe everything into a common unit, just to make sure we don't make a mistake. Okay. You could convert everything into meter or convert everything into centimeter. I think either way is fine. Okay. Yeah. So let's use centimeter a little bit better. So what's that? That's 10 centimeter, and then H is 100, right? Use a centimeter here. Okay, so now we figure out R naught, H naught now, and we can calculate partial V over partial R at 10 and 100. Okay, so here is your partial V over partial R. You just substitute 10 over here, 100 over there, and then do the calculation. Okay. So sometimes you leave it as it is, and then you can calculate in one shot. It's easier. Same thing for this term. So what does that give us? 1/3 pi r squared. Good. Yeah. Okay, so we've got these two terms nailed down. So now we get the last two terms. What will be the delta R and delta H? So this is where you got to keep alert. Okay, there's very common mistake for calculating delta R, delta H. Okay. So delta R, delta H is the change in each one of the variable. And delta R is the change, means you use the final value minus the initial value. So when you read the question, you have to clearly understand what is your initial value, what is the final value. Okay, do not reverse the order, right? Because you reverse the order, then you get completely wrong answer. So in this question here, the R changed from 10 to 10.1. So that's 10.1 minus 10. You got 0.1 centimeter. And delta H, right? This is where people make a mistake. Delta H changed from 1 to 0.99 meter, right? Meter. So your final H minus initial H, final should be 99 centimeter minus 100 centimeter. So you get a -1 value. Okay. So stick to the principle. What is the final value? What is the initial value? And now we got everything here. You substitute everything into, so all of these numbers substitute into this approximation formula. Your delta V is approximately 100 pi over 3 cubic centimeter. Okay. All right, that's the kind of questions that you probably expect in terms of total differential. In the past, this year we don't have midterm, but in the past for midterm question, I usually have the last question will test you on this total differential concept and also the approximation formula given a certain multivariable function. Okay, yeah. So anyway, any questions so far? Yeah. Okay, so before we finish off and start a new topic, let me ask you a multiple choice question and see if you have fully understand of all the multivariable function in here. Okay, so there's an MCQ question here. Okay, consider that we have a function z equal to f of xy. Okay. I'm going to give you 4 statements. Actually, the writing takes a bit of time. Let me find the picture and then paste it over here. Should have a picture somewhere here from last year. Yeah, there you go. A little bit larger. All right. So let's read it together. Okay. Given this function, number one, consider which one is false. First statement, values of this partial derivative at x naught, y naught is the slope of the tangent line to the curve intersected by plane y equal to y naught and the surface z and at x equal to 0. Okay, you don't answer, you don't have to answer, just think about it now and then answer at the end. Second one, partial f is an infinitely small quantity. And the third one, df is called the total differential of the function f of x, y. Last one, df tells us how much function f is related to the variations of x and y. Okay. So which one is false or which one or two is false? Yes. Okay, you think the first one is false? Anybody else want to? Yeah. Colin says second one. Right. Popularity test. Who would you like to vote for? Which one do you think? Anybody else a different? I guess everybody says this is correct. Okay. Okay. So the point here is which one is false for the first two. Let's focus on the second one. Partial f is an infinitely small quantity. If you recall, I have specifically said in the lecture, does this exist? It doesn't. No, it doesn't. Yes, it doesn't exist. It's not a quantity at all. Okay. So this is actually false. The first one is actually right. So that just give you the slope of the tangent line to the surface at that location, okay, for this partial derivative. Okay, good. So expect this sort of questions, okay, in your probably in your final exam too. Okay, very simple concept type of questions. Okay. Shouldn't take you more time. Just read it and then you should be able to get an answer. Any questions? All right, now let's getting away from multivariable function and then back to the vector concept. The first thing we're going to cover is called gradient vectors. Okay, so things are getting actually, I like the second half of this course, even though actually more than half, right, from now to the end, almost actually. The second half of the course has more applications, has more integrations of the concept we learned from the first half of the course. And also sometimes I feel like a more visually making sense. So let's take a look at what is gradient vector, okay? So let's consider a function of those three variables. And you can easily downgrade to function of two variables based on the results here. So this function three variables, and x is a function of t, y is a function of t, and z is a function of t. So, and now I'm going to, this is pretty much review. If I need to calculate the derivative of this w with respect to t, I can use the chain rule, right? So the chain rule is partial f over partial x, and then dx over dt, plus partial f, partial y, dy over dt, partial f, partial z, dz over dt. That's a result of the chain rule. And then I'm going to rewrite the results a little bit using vector notation. So basically, I'm going to create two vectors. The first vector is partial f, partial x, partial f, partial y, partial f, partial z. And that's the term, that's the coefficient, right, for each one of the term. And then I will create another vector with the second term, dx over dt, dy over dt, and dz over dt. I created two vectors. And as you can clearly see, if I do the dot products of these two vectors, I will get back to this the previous result. Right. Okay. So by doing this, okay, now we see that ourselves, we have a vector. This vector is a very special vector. So now we're going to define ourselves a vector. So basically, I'm single out this vector at here and define it as del f. So this inverted triangle and then function f symbol equal to this vector. Okay, so this is a new vector here. Okay, this is basically the vector we are going to talk about. And this vector is essentially called gradient vector. This del f is called gradient vector. There's so much usefulness for this vector. The del, I think I sort of covered in the past. So this guy here is pronounced as del, okay, or Greek letter nebula. So now you can see the del basically is an operator, okay? So del more precisely is defined as a vector operator. It's a vector, and each component of the vector is a partial derivative operator. So when you apply the del operator in front of a scalar function f, then you get a vector. And each vector's component is the first order partial derivative. Okay. So now it sort of concludes to this journey of the calculus from straight D to partial F, and then to this del F. So how we actually operate a scalar function, right? If it's a single variable function, straight D, multiple variable function, you're going to use the partial. And if you have a multiple variable function, now you actually can create a vector, which is called gradient vector, using this del operator. So we're going to talk about the meaning of a gradient vector, okay, shortly. But let's look at the operational wise. How do we use this del operator? It's very straightforward. Basically, you calculate the partial derivative, right? So let's take a look at a very, very simple example. Suppose you have this function here, and you are required to calculate the del f. It's pretty much an exercise of partial derivative. All right, so then all I need to do is to calculate each partial derivative and then put them together as a vector. So look at this function in here. So what do we get? So the first one, we get 2x, and then plus z over x. Partial f over partial y is 2y. There's nothing else. Partial f, partial z, negative 4z, and then plus ln x. All right, so that's the result of this del f operation, which give us the so-called grading vector. And sometimes we're also interested in what is this vector at a certain location. So if you have the actual xy coordinates, then you can plug in the value x, y, z into the vector. So we end up with 2 plus 1 and 2, negative 4 plus 0 here, which is 3, 2, negative 4. So the actual grading vector at this location is given by the 3, 2, negative 4. Okay. So this is a 3D vector, right? Okay. Now, often in time, it's hard to draw this 3D, not that easy as draw a 2D vector, but you have to think of this as a vector in 3D space attached to 1, 1, 1 point. Okay, so let me write it down first, and then I'll illustrate this idea using a simpler function 2 variables. So 3, 2, negative 4 is a vector, of course, is a vector attached to 1, 1, 1. So that's how you actually will visualize this vector. So where's 1, 1, 1? So first pinpoint that. If you have a computer, you'll easily do that. So 1, 1, 1 is somewhere here. And then this vector, I'm just drawing it. It's just not necessarily pointing this way. So 3, 2, negative 4. Right? That's how you illustrate this vector. So you can imagine if I pick a different point, then I will have a different vector, right? Then I can attach the vector somewhere else. So basically you can get a whole bunch of vectors. That's what we're going to actually cover. It's called a vector field. Okay. In this case, is a grading vector field. Okay, so kind of running out of time, but I started a little late, but that's okay. I will illustrate this concept using a little more simpler, using function 2 variables, so then we can see how do you generate a grading vector, how do you properly draw this in a 3D graph. Okay, any questions? All good? All right. Hey, we'll see you on Friday. Bye, Colin. Yeah.
Hello, doctor.
Yes.
I had a question about the multiple choice thing earlier.
Yes.
About the first one, because
Yes.
I was just confused because it said,
Yeah.
oh, sorry about the mess.
It's okay.
It gives the slope of the tangent line to the curve intersected by y equals by the plane.
Yes.
But I thought that y equals y naught was a line and not a plane.
No, why? So you got to think in the 3D sense, right?
Mhm.
So, for example, right? If I draw y equal to y naught, this is y, this is y naught here. So this is y equal to y naught, right? This is a line, okay? But in 3D,
Oh, I see.
it's a point.
Gotcha. Okay.
Yeah.
Thank you very much.
No worry, yeah.
Last class,
Yep.
we were going over the chain rules, case 1, case 2.
Oh,
and
I
then-
missed the case 3.
Yeah, we didn't finish case 3.
Okay, well, case 3, yeah, that's right.
Is it in the notes online?
It is in the notes online.
Okay.
I mean,
okay.
case 3 basically is, so you see case 2, case 2, right? So function 2 variable, and each variable is another function, another 2 variables.
Yeah.
Right? So then what I'm trying to cover for case 3 is you have function 2 variable, then each one of the variables is a function of another 3 variables.
Oh, okay.
So it's basically I just extend by
one
for
variable.
one variable.
Okay.
And then the chain rule wise, formality wise, it's the same, right? So if I take a partial f
over the final variable. You have 1, 2, and then plus one more term.
Okay.
Yeah.
Okay. And then I wasn't sure where we
Got C equal
got
to
the C
negative
equal
1.
to -1.
So you first of all, you need to consider this Z here is the X here. That is L here.
Yeah.
Right? You see, when you have a plane, you have a Z. For example, I have a plane Z equal to something,
Yeah.
right? So in this case, I use the symbol L.
Okay.
Right?
Okay.
So if you move the L to the same side of everything, then you got a negative L minus a plus this term, right?
Okay.
So then if I write it into this format, basically I have what? Minus brackets L minus this F there. Does that make sense?
Yeah. So
So
then you
that-
get -1.
That's right. Yeah.
Okay. Okay.
Good.
Thank you very much.
No problem. Yeah. Hey, come in.
I was just wondering where
Yeah.
the -1 came from in this.
Oh, yeah. So this is a plane. You missed a plus sign. Right? This is a plane, huh?
Yeah.
So the one we have it up here,
Yeah.
you have to think this is symbol L, but this L here basically as this symbol Z,
Okay.
right? You know, you have a plane. When you have a plane, you can always write the Z equal to something, right?
Yeah.
And in this case, I have instead of calling Z, I call it L equal to something.
Okay.
So then if I move this L of X, Y to the same side, to the right side here,
Okay.
it becomes negative, right?
Okay. Yeah, that makes sense.
And then you take the negative sign out, bracket, and then L minus this F.
Okay.
Yeah.
Yeah. Okay. That
Yeah.
makes sense. Now.
Yeah, no problem. Yeah,
All right.
yeah.
Awesome. Thank you.
Bye. Yes.
Just a question is why partial F doesn't exist?
It's just how I would say it's how it's defined, right?
Mhm.
I mean,
It's like we use it, but it just doesn't exist in real life.
doesn't exist means you cannot quantify it.
Hmm.
So for example, the delta F, it's how much? It's that much, right?
Yes.
And df, you can't use this anymore, but you know it's an infinitesimal small quantity.
Yes.
It's still very, very tiny small quantity. But then partial F, there's no such thing. You know, it's not defined like this.
We're just using it to find the slope.
Exactly. We use it, we cannot use it alone.
Mhm.
We have to use partial F over partial X, for example, right? To get you something. Yeah. So, yeah.
Now, the other one is, so the last thing that you explained us
Mm.
was this, right?
Mm.
So the computers that we use to make planes, do
Mhm.
they use like this equation to make planes in 3D for us?
Oh, to make plane.
Because if we just use like all the points,
Mm-hmm.
right?
Mm.
And then there will be a vector that will exist from that point. Will that make a plane? Or like, sorry, not a plane, but a surface.
The surface? No, actually, you're onto something, but not this case, because in this case we get a function of 3 variables here, right?
Yeah.
Yeah, we got function 3 variables. You technically you cannot graph this out in 3D space.
We can.
You can't. For function 3 variables,
Mhm.
you cannot graph it out in 3D space. But you can do that for function of 2 variables.
Can
right?
we not do it in 4D though?
Yes, you can, but
Like,
but-
adding a frame at every moment?
sure you can, but I cannot draw it in a 3D real world.
Oh, yeah.
You know what I'm saying,
We
right?
can just
What is 3D?
imagine it.
You can imagine, exactly, yes. So basically, it's not like you draw a curve. Oh, look, it's the curve, right?
Yeah.
Here is a surface. Yeah,
What if we initialize one point,
yeah.
just like we try to find the slope of line or not, sorry, the
Hmm.
equation of line?
Mhm.
We put z is equal to t, right?
Uh-huh.
Right?
Uh,
So if we just do that
Yeah.
with this,
Yeah.
so we can make one, like that
Uh-huh.
plane at one point,
Okay.
or like a t,
Yeah.
or let's say one point, just keep it constant.
Yeah.
And then we keep replacing the numbers, and then we get a figure, don't we?
That figure is still not the figure for this function,
Oh,
right?
it
what he's
won't be
saying
the
is-
figure?
Huh?
It won't be the figure?
No. So look, remember when we have a function 3 variables, remember when we can visualize it is what? using level surfaces.
Yes.
But level surfaces, it's still not the actual what this function look like. Because basically, all you're thinking, what does it look like?
Yes.
You cannot present what it looks like. You know what I'm saying, right? It's not a tree, it's not a person, it's not a real object.
Okay.
Because you cannot visualize it in 3D world. You see what I'm saying, right? That's unfortunate. Multi-variable, right? Or multi-dimensions. So if if human being evolve to
4 dimensions.
4 dimension,
Then you can travel at
then
speed of light.
you can probably visualize, right? Yeah.
I see.
So
Okay.
like you watched the movie
Interstellar?
Interstellar, right?
Mm.
Yeah. So that's why alternative way is you try to visualize it, but you know that the word is misleading, right?
Hmm.
You try to visualize it through an indirect way, which is the level surface. So you let the W equal to constant, and you got a surface. You get another constant, you get another surface. So in your head, you visualize, okay, got this surface. All of the surface of like layers stacked together.
No, not stacked together. I don't think they will be stacked together.
I mean,
Because as soon as we change the variable,
yeah,
it's different.
exactly, right? So they're not discrete, as you
Yes,
said,
yes.
right? You know, like the simple example, x squared plus y squared plus z squared.
Sphere.
W, sphere. You
Yeah.
put the any constant of sphere.
Yeah.
So I could,
bigger and bigger and bigger.
yeah,
sphere.
exactly, right?
Yeah.
If I say it's a layer like onion, okay, but it's not really that case, right? You technically have infinite layers.
Right.
But it's not a sphere.
Yeah, it's not a sphere. Yeah.
Yeah. So we cannot visualize that, but you can certainly visualize this.
Because we are in 3D and this is
Yeah.
3D.
And this is how you were just saying, right? How do I plot this surface using, for example, MATLAB? And MATLAB, how it does is probably, you create a vector for X, you create a vector for Y. Then you plug in each one of the vector into the function, and you got a whole bunch of values for the Z, right? Then the MATLAB basically take all the coordinates
Yeah, points it.
and intersect, and then give you a surface.
Thank
you. Yeah, no
I just
worries.
had a doubt in visualizing partial derivative xy.
Hmm.
Like partial derivative xy and partial derivative yz. How do you visualize that?
What with partial f and partial x?
No, partial derivative of d xy, just xy. X.
And you're right.
Partial derivative xy, like it's there in the notes. Yeah, I'll show you the notes.
You might notes?
Yeah.
You need to practice on how to write a partial derivative.
Yeah.
Let me close out here first.